now let's talk about how to calculate confidence interval for mean, how to calculate these parameters for the sampling distribution of average values. And I will start with large sample. We will discuss why large sample a little bit later, and then we will talk what to do if you have a small sample size. Okay. So let's start with the example I've shown before. We have 50,000. We have a population of 50,000 persons, and that's how height of the persons is distributed. I use normal distribution, but we already found out that it will work for any distribution in this case, right? So this is the average and standard deviation for my height values. So this is height values. This is x values, right? And then what I did almost the same thing. So I took many samples, 200 samples of the same sample size, but now I changed the sample size. I started with a sample size 6. So this is 6, okay? So this is the distribution of all average values, of 200 average values for my sample. And then you can see the confidence interval and the theoretical distribution, the true theoretical distribution, okay? If I calculate the average and standard deviation for the m values, so these ones, you can see that the average is pretty close to the real one. And the sigma, the standard deviation for mean values, is about 4. You can see that the spread is pretty large. Sometimes I've got 164, sometimes I got 185. It's pretty large from the true average, right? But the sample size was small, okay? If I repeat this again, and in this case I have sample size 30, you can see that the distribution is more narrow. And even though the average is almost the same for these m values, so these are m values of my samples, the standard deviation for this distribution is almost twice, or more than twice smaller, okay? Now, if I repeat it again, and now my sample size is 200, now I have even more narrow distribution. And you can see that, once again, the average is about the same. It's about true average of the population. And now the distribution of m values, distribution of mean values becomes smaller and smaller and smaller, okay? So there is a very certain rule about how distribution of mean values for a random sample and distribution of real values in your population relate to each other. And that's the formula. Okay, so here it's a distribution, standard deviation for your population for all values, okay? This is the sample size. This is the sample size. And this is it's uncertainty for average values of your sample. So it's how far the average value for a given random sample can go from the true average values. Now you can see that we have n in denominator again. So it means the larger n is, the smaller uncertainty it is. Okay. For example, if n is equal to 100, n is equal to 100, then it will be sigma over 10. Okay. But if n is equal to 25, it will be sigma over 5. So it means in this case, it will be twice smaller than this one, okay? So I should write probably not like this, but like this, okay? Twice smaller than this one. So the larger sample, the smaller uncertainty in your average values, okay? I will tell it exactly a little bit later, but this uncertainty, the standard deviation for average values, is called standard error. Standard error of mean, okay? So standard error is uncertainty for statistics, while standard deviation is uncertainty for the values. So that's the biggest difference. When we talk about standard deviation, we talk about values. When we talk about standard error, we talk about the uncertainty for the statistic. In this case, it's average. Okay. Now, we can calculate. We know that the distribution is normal. We know it's situated around the true average. And we know the standard deviation for this distribution, the standard error. So it means we can calculate this confidence interval using this formula where z depends on the confidence. For example, for 95.5%, 95.5%, z is equal to 2, right? For 95%, z is equal to 196. And then you can use the ICDF function to find z for a given probability, okay? The problem here is the following. To calculate confidence interval, we need to know the population parameter. We need to know sigma, and we need to know the average of the population, okay? So how to get rid of that? Well, let's start with the average, with this one, with the point estimate, okay? In fact, you don't need it. I'll show you why. So the intuition is following. If you get back, this z sigma over square root of n gives you the uncertainty, how far the length of the interval, right? How far your values can go around the true parameter. So if you know this, that's enough. Let me show you the example. So this is the true average value, and this is the confidence interval, which of course we need still sigma to find it, but let's say we know it. Okay, so how big the uncertainty is. Now let's take, we took a sample, this one. Average of this sample is m. Now we don't know mu, but if we know the size of the interval, we can just use it around the m, because the mu will be inside, and that's what we need. We need to find an interval where mu will be inside. Okay, so I took another sample. Now m is here, but still, because we know the size of the interval, the true mu will be inside in most of the cases. So if we calculate it for 95% confidence, in 95% cases, the true mu will be inside this interval. Okay, so we don't need to know mu. We can estimate mu as an interval if we know the size, the uncertainty. Okay, that's just another example. So we have m. It's pretty large from mu, but because we know the size of the interval, we can build this interval around m, and mu will be still inside, and that's what we actually need to get. Okay, so that means, like a very simple example. Let's say we have a strange voice from heaven that tells us that standard deviation for population is 5. Okay, and now even though we don't know anything else, we can just calculate this as a standard error. We know that, let's say the sample size is 16 in our case. So if we take 16 persons random, so that will be the standard error. That will be the standard error. And now that's the error margin for the 95% confidence interval. I just took 196 standard errors. So it just gives us 2.45. Okay. So it means that, for example, we took a sample and average is 173. Because we know the standard error and we know error margin, we can calculate the confidence interval, and that's the confidence interval. Okay, it tells us, well, the population average is somewhere between 171.55 and 175.45. Okay, and you see that the true population average is inside, so that's correct. That's correct. We took another sample. Now it's 176.5. We calculate. We know the error margin, so we can calculate 95% confidence interval. That's the interval. So it tells us we don't know the true average of population, but it's somewhere between 174 and 178.95. And it is indeed inside. So 175 is inside, and that's what we actually need. Of course, in some cases, if you are unlucky, in this case it's 5%, you have 5% chance that you will have something like this. So you got a sample, you calculate confidence interval, and you see 168, 55, 173.45. So the true average is somewhere here. So, but it's only 5% chance. If you want to decrease this chance, just calculate confidence interval for 99% confidence. Now the question is how to get sigma. Okay, you still need sigma to calculate the interval. Well, you know about something about representativity and randomness. The more objects you have, the better. Okay, so in fact, if you have more than 500 objects, well, 500 is just, it's not a fixed rule, but if you have many, more than several hundred objects, the standard deviation for your sample will be very good estimation for the standard deviation of your population. So in fact, you can substitute sigma over square root of n with s over square root of n. Okay. So you don't need, if you have a big sample size, several hundred values, in this case you don't need to know anything about population, because the sample size is big enough to get a good estimate of sigma. And then you can use normal distribution and calculate error margin like we did before. Okay. So this is also called standard error of mean. So in fact, it's just a standard deviation for your mean value. So how far your mean values can go around the true mean. So what it means? It means that we have a very simple formula now to calculate confidence interval. So that's the confidence interval for the population. We need to know S, we need to know N, it's a sample size, and we need to know M. So average and standard deviation of our sample and the sample size. Usually we of course know that, okay? And then you use Z depending on the confidence level. You remember that if confidence level is 95%, it's 196. If confidence level is, for example, 99.7%, it's 3. Okay, so the more confident you will, you want to be, the larger confidence interval, the larger confidence interval is. Okay, and you can always use ICDF to find the Z values for any confidence but it works only if sample size is 500. Well, what to do with confidence intervals? Well, first of all, it's a good estimate, so you can say something about population. You can also represent the confidence intervals using error bar plot. For example, in this case, you see I have chloride content in Wade and Ribe, and I have an error bar plot. This is the average of my sample, and this is confidence interval. In this case, I use 95% confidence interval. 95% confidence interval. Or you can do it like this. So you have bars, which gives you the average value, and then you have these error bars that gives you how big the uncertainty for the average value is. Okay. Unfortunately, R doesn't have a direct function that calculates it, so I wrote this function for you. It's called error bar, and every time you want to read this to use this function, you need to download this code from the Moodle or from EDX, and then you use function source to get all functions from this R code, R script, available for you. And after that, you can just call error bar or like this. Okay. Just practice a little. I also will show how to use this code at the end of this lecture. Now, let me show you another simulation. It shows you how good this estimates when we use sample statistics to estimate the confidence interval work for the different sample size. Okay. This is my population again. I have 100,000 values in this case in my population. This is the average of my population, and this is the standard deviation. So you see, it's pretty close to 175 and 4. Okay. Now that's my first trial. I took 3 different samples. In this case, I have sample size 10. In this case, I have sample size 50. In this case, I have sample size 100. In each case, I calculated confidence interval using the statistics of my sample. So I used standard deviation of sample instead of sigma, and average of the sample. Okay, so you can see that's the true value, and you can see that in this case all confidence intervals contain the true value inside. So in this case it worked very well. If I repeat it again, I will get this one. Now you see that if you have sample size 10 is outside, so we don't have the true value inside. But for sample size 50 and 100 it still works, even though you can see that the sample size 100 have a pretty narrow interval, but it works well. Okay. If we repeat it again, in this case, you can see that both samples 10 and 50 don't have the true value inside, but for 100 it still works. Okay. So you can imagine that if we repeat it like 100 times, well, for the small sample size, most of the time it will not work. For 100, it will work maybe not 95% of the cases, maybe 90% of the cases. But if you increase the sample size to like 500-600, it will work almost in 95% of the cases if the confidence interval is for 95% confidence. Okay. So once again, this estimation works well for big sample size, but for small sample size, it doesn't work. So we need to find another solution for that.